Hello everyone, welcome to class 6. So, we will again continue from where we left off in the last class. In the last class we were looking at some of the nonlinear properties, and in particular we were looking at second harmonic generation. It is an optical property, right. Again, if you go back to the title of the course, we talk about electrical, electromechanical and optical properties, but we look at a common framework that unites all these things despite them being seemingly different, right. So, what do I mean by that? I will first talk about that in the first part of today's lecture. So, the optical property we were looking at last class was second harmonic generation, where you shine light into a material. This light is oscillating at a frequency omega. The response that you generate inside the material is at frequency 2 omega and also at frequency omega plus omega, that is, and frequency omega minus omega, which is the DC frequency, right. The 2 omega frequency can be used as a what are called these nonlinear crystals from which you shine light and you generate light of a higher harmonic, right. So, that is a second harmonic generation, and the tensor, the property of significance is chi I j k, which is second harmonic response tensor, and the same tensor also is dictates how the DC polarization response of the material is, and this DC response can be used to separate carriers and then create a photovoltaic effect, right. So, it is like two eyes of the same second order effect. So, one is a 2 omega response, one is an omega minus omega or a 0 frequency response or a DC response. The DC response can be used functionally to separate charge carriers and create photovoltaic devices. The second harmonic response can be used to generate light at higher harmonics, right. So, you shine light at omega and then you can generate light at 2 omega and so on and so forth, right. So, this is commonly used in lasers, for example. If you want to generate double the harmonic, you send the laser through a nonlinear crystal and then you generate light again at 2 omega frequency. Okay. So, now okay, so let me again so start with so what are the two third rank tensors that we spoke about so far, right. So, we were looking at third rank tensors, couple of important third rank tensors or property tensors. Again, when I mean tensors, so I mean property tensors, but there can be tensors like stresses and strains that are not property tensors, right. So, those are called field tensors. Stresses and strains are called field tensors. We'll talk about it in this class. So, third rank tensors. So, one of them is dijk. This is the piezoelectric tensor. And the other one is chi 2, or I must write chi 2 ijk. The indices give away that it is a second rank tensor, but just to emphasize the fact that this is a second order effect, I write chi 2, right. So, it is the chi 2 response. So, chi 2 is the second harmonic response, second harmonic generation response tensor, right. These have seemingly different origins, right. So, dijk is I stress the material and I generate charges. These are sort of static charges, or okay, so there is nothing optics about this, right. So, there is no optics in this. This is an electromechanical property. Whereas chi 2, it is a, and this is a linear effect, right. So, I stress the material and so linearly so I multiply the stress that I apply with this dijk to get my polarization, right. So, it is a linear effect, right. So, it describes a linear property of the material. Whereas, the second harmonic generation response, right. So, this is an optical response. There is no mechanics or electronics associated with it, no mechanical, no mechanics, right. So, this is a different property altogether. One is an optical property, one is an electromechanical property, and this is a nonlinear property. okay, completely different quantities, right. However, seemingly, so they are related by one fact that both of them are third rank tensors. The only relation that these things have is that these two properties are third rank tensors, right. Sorry. Right. So, both these properties, the only mathematical structural equivalence is that they are third rank tensors. Physically, they have different origins, they describe different phenomena. One is an electromechanical property, one is an optical property, one describes, one is nonlinear, describes a nonlinear response of the material, the other one describes linear response of the material, and so on and so forth, right. So, now I am going to say that so we can despite them being so different, right. Now, there is a fundamental, let me say, theorem, okay, or a principle, right, given by Neumann, which says that the property of materials, property meaning property tensors of a material, should at least have the symmetry of the point group of the material. Now, this does not make sense right now. I am going to go into point groups to actually point group of the material. I am going to go into what are point groups of the material to actually make sense out of it. But it just says that if material has a certain symmetry, right. So, if I rotate the material by 90 degrees and then see that the material is exactly the same, nothing changes, right. So, nothing visibly changes. So, I have a material, I rotate it by 90 degrees and so there is complete equivalence, right. So, then I say that this material has some sort of what is called a four-fold symmetry. Okay. So, we are going to go into symmetry, that is going to be the next from next class onwards, right. So, right, and this symmetry can be discussed as what are called point groups, etc., etc. But in general, the properties of the material, which are also tensors, right, would follow the symmetry of the material, right. So, what does that mean really, right. So, if my material has what is called, I mean, it becomes clear later on, right. So, I just wanted to introduce this idea so that we know what is coming on later on. If my material has what is called centrosymmetry or inversion symmetry, that means if I have something, some sort of an environment. So, this is the origin, right, and I have some kind of an environment in my material at position x, y, z, right. Now, I invert it to minus x minus y minus z. The environment around minus x minus y minus z is exactly the same as the environment around plus y plus y plus x plus y plus z, right. So, if I put a dog here, for example, right, or if I put my instead of a dog, okay. So, if I put my right hand here, right, 0 0 0, I put my so right hand here, excuse my drawing, but so my right hand may be actually a bit better than that, but okay. So, so I am putting my right hand facing up, and on the other side I should exactly see the same environment, means I have the same object, but it is inverted, right. So, I have a left hand that is coming here, right. So, all the points of this right hand are transforming, right. So, I have the same object at minus x minus y minus z, I have this object at minus x minus y minus z, right. So, that gives me a left hand, that gives me a so if I have right hand pointing up, I have a left hand pointing down here, right. So, I have a left hand that comes up here, right. So, if I have both these objects in my material, right. So, in my material of consideration, then I call that the material has some sort of centrosymmetry. It has inversion symmetry, right. I can invert the material about this point and nothing changes, right. I can reverse everything, right. So, I can put this here and put this there, but nothing changes, the material remains the same. Okay. So, that is what is meant by saying my material has centrosymmetry, right. Now, if my material has centrosymmetry, what I mean by material having centrosymmetry is so the transfer, okay, so the transformation matrix for inversion, right. So, I am going to invert the material, which means I take every point x y z to minus x minus y minus z, right. So, what is the transformation matrix? This is a transformation operation. So, the transformation matrix is minus 1 minus 1 minus 1 0 0 0 0 0 0, right. Okay. Now, when I use this transformation matrix and transform every point in the material, there is going to be absolutely no change, right. So, the material exactly looks the same as when it was not transformed, right. So, transformation has shown no changes, right. So, the structure or all the objects inside the material are exactly at the same exactly look similar, look the same. Okay. So, that is what is meant by the material having inversion symmetry, right. Now, let us look at how my third rank tensor transforms because of a transformation which is Aij, right. So, I have Dijk that transforms or D dash Ijk, right. That transforms as per Aij, right. So, Aij Ai, I am using a transformation matrix, right. So, AIL, AJM, AKN, DIJK, right. So, this is how my third rank tensor would transform. Now, the only components that will survive are the diagonal components, because the off diagonal components are anyway zeros, right. So, I have AII, AJJ, AKK, DIJK, right. Now, AII, AJJ, AKK, this is a minus 1, this is a minus 1, this is a minus 1. So, I have this to be minus DIJK. Okay. So, if I just invert any crystal, that crystal does not need to have inversion symmetry. Inversion operation, right, and I measure Dijk, right. So, after inversion. So, before inversion, if I measure D property as Dijk, after inversion I would measure it as minus Dijk, right. So, before inversion if I measure, let us say D111 as some 10 picometer per volt, right. So, that is the unit of this. Okay. So, we will look at it later. After inversion, I do the same measurement, but I had inverted the crystal now. I will measure D prime 111, because this is in a new coordinate system, right, as minus 10 picometer per volt, right. This is in any crystal. Okay. Now, let us come to the case of centrosymmetric crystal or case of a centrosymmetric crystal, or my material has what is called inversion symmetry. If my material has inversion symmetry, if I have inverted the material, nothing should change. Whatever I have measured before inverting the material, after inverting the material, I should measure exactly the same thing. No one knows, right. So, if I have inverted the material without your knowledge, and you measure a property to know whether the material has inverted or not, if there is inversion symmetry in the material, you can never say whether I have inverted it or not, right. So, that is meant by having the inversion symmetry in the material. So, after inversion symmetry, after inversion operation and before inversion operation, the material should exactly be the same. Material is exactly the same means its properties are also the same, nothing changes, right. So, which means the properties are also the same. That means after inversion, whatever I am going to measure as d dash 111 should be equal to or d dash ijk should be equal to before inversion d ijk. Okay. So, this is by virtue of having centrosymmetry. Inversion symmetry. Right. All right. So, now I have a scenario by virtue of having centrosymmetry, I have d dash ijk equal to d ijk, but just by virtue of transforming the vector, right, by inverting it, d dash ijk should be equal to d ijk. This is just by inverting the coordinate axis, right, or transforming the coordinate axis. Now, I put these two together and then what do I have? I have d ijk equal to 0. The only way this is possible, right, if I invert any crystal, whether the crystal has centrosymmetry or no centrosymmetry, d ijk should be equal to minus d ijk, d dash ijk should be equal to minus d ijk. Now, if there is centrosymmetry, however, d dash ijk should be equal to d ijk, right. The only way this is possible is if d ijk is equal to minus d ijk, that is equal to 0. Okay. All right. So, what did we get? Now, did we use any knowledge that what I am looking at is piezoelectric tensor? No. All we have used is the knowledge that the tensor is third rank tensor, right, and third rank tensor transforms as d ijk equal to minus d ijk under inversion. Okay. So, we can actually make a general statement that if a material is centrosymmetric, all the third rank tensor properties vanish or do not exist. This material will not have any piezoelectricity, this material will not have. So, no piezoelectricity, no what is it, second harmonic generation response, right. These are seemingly different properties, one is an optical property, one is an electromechanical property. Just by the virtue that these are actually third rank tensors and by virtue of the material having a centrosymmetry, you can say that seemingly unrelated properties do not exist, right. So, I am trying to get a connection just based on the mathematical structure of these properties. You can say that okay, so so I give you a crystal, I say okay, so can you measure the piezoelectric coefficient of this crystal, right. So, I give you something like sodium chloride salt. The first question you ask me is there centrosymmetry in this crystal? If there is centrosymmetry, and then I give the same crystal to somebody else and I say okay, why do not you measure the second harmonic generation, right. The first question both of you should ask me, although one comes from an optics background, the other one comes from a mechanics background, is does this crystal have centrosymmetry? No, no, then I will measure, right. If it has centrosymmetry, then okay, you give me back the crystal and then say okay, no point measuring anything because the properties will be 0, right. So, symmetry imposes that the property is going to be 0. These are seemingly different properties, but the only relation is they both are third rank properties. Okay. Now, the same thing so I want my tensors to transform using this law, right. So, the tensor d dash should be equal to tensor d minus d, right. So, that will also happen, right. So, how does a first rank tensor transform? For example, d dash I equal to minus d I, right. This is for a first rank tensor. Okay, so let me just write t, right. So, T dash should be equal to minus T, right. So, that is the imposition by inversion, and that will happen for all odd rank tensors, right. So, if I have a first rank tensor, sorry, T dash I equal to minus T I, right. If I have a third rank tensor, T dash I j k equal to minus T I j k. If I have a fifth rank tensor, I do not even know what this fifth rank tensor, some nonlinear tensor, T dash I j k L m equal to T minus T I j k L m, right. So, whenever this is valid, and this is valid for all odd rank tensors. So, odd rank tensors vanish under inversion symmetry, and these odd rank tensors need not be related to each other in any way. You see, I have not used any property of them, I have not used any knowledge about the material here, right. I am just looking at the mathematics, the mathematical structure of the tensor. Say I have realized that property is a tensor and piezoelectricity is a third rank tensor, second harmonic generation is a third rank tensor, pyroelectricity is a first rank tensor, right, and there are other higher order effects which give me fifth rank and seventh rank tensors, etc. All these are 0 if I have centrosymmetry in the crystal, that is it, right. So, if I give you sodium chloride that has centrosymmetry in the crystal, all these properties will be 0, okay. So, I do not need to know anything else, right. I just need to know sodium, forget sodium chloride, at least I gave you the chemistry. I do not even give you the chemistry, I give you a black box and say this black box has centrosymmetry in it, right. The black box crystal has centrosymmetry in it, then all these properties vanish, okay. So, that is the beauty about, so we will expand about this once we know more about the other operations, right. It is not just inversion, we have to look at other operations also and then look at how these tensors transform, right. So, so that is what we are going to do from next class onwards, but this is just a teaser of what is about to come, okay. All right. So, I will again do inversion, I will again remind you that so this is what we have done in class 6, okay. So, that is fine. Now, let us look at so okay, let us look at what can be the other nonlinear tensors, right. Now, I told you that I have a polarization which is generated when I have I am just changing gears here. So, I am going back to some of the other nonlinear tensors because I want to go towards stresses and strains. So, polarization as a function of stress j k is d I j k x j k, right. So, d I j k is the piezoelectric tensor. Now, I can so I can write another effect where instead of applying stress, and so this is called direct piezoelectric effect. Where I apply stress, I apply some piezo and I get some electric effect, right. So, I apply stress and I get PI, polarization, right. Now, there is what is called a converse piezoelectric effect, where I apply electric field, right, in the I direction and I get strain in the j k direction, right. So, this is what is called. Now, I know that I have inverted the indices here. So, I belongs to the electric field, j k belongs to this and then I wrote the same d, right. So, there is a reason why I am writing this, but in general this is also a piezoelectric effect, right. This is called converse piezoelectric effect. So, what is the cause? The cause is the electric field, and what is the effect? The effect is strain. So, I apply electric field in a material, I apply voltage to a material and the material will expand, right. So, the material will start let me use this pen, the material will start expanding and contracting, right. So, it goes up, comes down depending on if I apply an alternating signal, right. So, if voltage is positive, material expands, voltage is negative, material contracts and so on and so forth, right. So, that is so that also has a coefficient and it turns out that these two coefficients are the same, we will prove that later, but there is a reason why I wrote this equation like this, but this is essentially a piezoelectric effect. This is also a piezoelectric effect, right. So, I am generating strain by applying electric field. Okay. Now, I can also make this non-linear, right. So, what is the point of just making it linear? So, x j k is something that I am generating is d I j k e I. However, I can also have a relation with respect to E okay. So, I can also have a relation with respect to, I am just going to write it as E I two other components, right, E m E n, but then the tensor I will have j k m n, right. So, this is again E m E n will transform like a second rank tensor. The strain I am generating is second rank. So, the m j k m n that I have, right. So, this is a fourth rank tensor, but it is a non-linear, it is describing a non-linear property, right. So, in other words, if I just have yeah. So, E equal to E 1 0 0 again, right, and then so then the second rank x would be E 1 square times m 1 1, but I can generate x in I j, whatever be that I j 1 1, right. So, this is just the, so I am ignoring the first rank dependence, it is just the second rank dependence, right. So, this m is a nonlinear property and this m is what is called electrostriction, right. Now, if my material is not piezoelectric, so let us say my material is centrosymmetric, which means my d I j k is equal to 0, right. So, I write x I j is equal to some 0 plus ideally if I am just looking at first order terms, right. So, a linear response, then x I j should be 0, right. So, in non piezoelectric materials there should be no strain when I apply an electric field. Non piezoelectric have no strain when electric field is applied, right, if I am assuming just a linear response, right. But I give you a non piezoelectric material and I apply strain I apply electric field and I generate some strain, right. So, that is most likely, but if a centrosymmetric or a non piezo material generates strain x I j by electric field, it is because of higher order effects, right. And the immediate next order after piezoelectricity is electrostriction. Now, electrostriction is a fourth order tensor, fourth rank tensor, right. So, this is an even rank tensor, so it exists, it is non-zero or it exists, let us put it this way. Symmetry does not impose that it should be 0, it should exist even in a centrosymmetric crystal. Okay. So, now the black box I gave, I am going to modify the problem. I give you a black box and you ask me the question, or I give you sodium chloride and you ask me the question, the piezoelectric guy, right. So, the piezoelectric person, Alright. So, do you have centrosymmetry? And then I tell you yes, I have centrosymmetry. Then you can either give me back the crystal, or you can take the crystal and measure. You look, I may not be able to measure the piezoelectric coefficient, because there may be no piezoelectric coefficient, there will be no piezoelectric coefficient. Symmetry imposes that there is going to be no piezoelectric coefficient. But I am not saying that by applying electric field I will not generate any strain. I can generate strain, but this can be because of higher order effects, right. So, I will be able to measure something like electrostriction, right. Is it okay with you, right. So, that is the question that you ask me, and I say all right, fine, go measure. I will give you, you can apply an electric field and measure strain and tell me what is the electrostriction coefficient of this material, right. So, yeah, I mean the higher orders can exist even if the piezoelectricity does not exist, okay. So, with that, so we have been talking about stresses and strains, right. And I have been tacitly implying that stress xij and strain xij, small xij, these are also second rank tensors. But stresses and strains are what you apply and what you measure, they are not material properties, right. So, stress and strain are what are called matter tensors, are what are called field tensors. Whereas, the properties that you are measuring, which is the so something like chi ij, which is the susceptibility, or sigma ij, right. So, these are what are called matter tensors, okay, or kij, k being the thermal conductivity, okay. So, we will actually so if I write a stress tensor, then right, stress tensor looks something like this: x11, x12, x13, x21, x22, x23, x31, x32, x33, right. So, in the next class we will start by understanding what the stress tensor and strain tensor is, okay, and strain tensor is xij is equal to x11, x12, x13, x21, x22, x23, and stress, traditionally people have told us that stress is just a force applied on an area, right. So, force has a direction, area also has a direction, right. So, normal vector, and so the xij tensor will be given as force by so F has a direction by A, but that has a normal vector that has also direction, right. So, ij is the tensor that gives you this. Okay. Similarly, strain, people have suggested that strain can be measured as the dx by or du by the initial length du by L, right. So, we are actually going to look at stress and strain in the next class, but so these are actually field tensors. This has got nothing to do with the material property. Now, you apply stress on the material, and the compliance is the material's property. Stress itself is not material's property, strain itself is not material's property. I can change these things, these are external parameters that I am doing to the material, okay. So, we will start with what stress and strain is, just to understand that these are actually some properties of stress and strain tensors allow us to understand so again the mathematical formulation of these higher order tensors, right. So, for example, if I look at a tensor which isCijkl, right. So, the stiffness tensor should ideally have 3 times 3 times 3 times 3 power 4 elements, right. But because of some symmetry properties of stresses and strain tensors, that these the compliance and the stiffness tensors relate, right. So, it relates stress to strain. So because of some sort of mathematical symmetry that you see in these field tensors, the number of components of these compliance and stiffness tensors reduce, right. So, we will start there and then go into material symmetry, right. So, in the next class, yeah. So, thank you very much. So, I will see you again in the next class.